Algebra 2, 7-1, graph exponential growth functions. So an exponential function can be written in this form: y equals a times b to the x power. So what we need to notice here is the variable is the exponent. So it's not like x squared or x the third. I have b raised to the x power. So variable is the exponent. If I have an exponential growth function, that means my a is greater than 0 and b is greater than 0. And the growth factor is b. So on our next page, we are looking at the general form of one of these functions. So what we're going to do is we're going to look at just y. It says f of x equals b to the x power, but we'll look at just y equals b to the x power. We're just going to make a quick table, an xy table. We'll look at when x is -1, 0, and 1. And it's tricky because b could be 3, it could be 5, it could be 2. And so it's going to be a little bit different for each problem, but we'll just get an idea of what's going on here. So I can put in any number for x, right? I can have negative numbers, I can positive numbers, I can have 0, I can have fractions. So my domain is all real numbers. I'm going to go ahead and fill that in. If I raise b to the -1 power, that would be a reciprocal, so I'll have 1 over b. b to the 0 power is going to be 1. b to the first power is just b. So I'm going to go ahead and plot 0, 1. And then I'm going to plot a point somewhere over here randomly, and I'm going to call this, oh, I guess it needs to be 1 comma b. So I can't put it too random. It needs to be on the line where x equals 1. So let's just say it's here. So this will be 1 comma b. Normally I wouldn't label it, but this is going to be b units. And then 1 over b will be somewhere over here. So it's going to be a fraction. So you can see that our exponential growth functions are going to have a shape like this. It rises from left to right. And again, this is for exponential growth. Rises from left to right. When we look at decay, it will fall. And then we might also notice here that our x-axis is like an asymptote. So as I look at x is -2 or -3 or -4, those smaller and smaller values of x, I'm going to get a smaller and smaller fraction for my y value, but it's not going to ever reach 0. It's not possible to raise something to a negative exponent and get 0. I just get really small numbers. So my x-axis, or y equals 0, is an asymptote. So asymptote means we get closer and closer to that, but we don't actually touch it. And that means that my range is going to be anything above that. So my range would actually be y is greater than 0. So it can't be 0, it can't be anything negative, it's going to have to be above 0. So we're going to look at actually graphing some with numbers. So I think this b thing can be kind of hard to follow. We want to look at the general shape of the graph, but it's really a lot easier to do if we have numbers. So for our first one, we're going to graph y equals 5 to the x power. I always start off with a table. A lot of these are not graphable points, I call them, where maybe we can't really accurately graph them, but we're going to put them on our table anyway. 5 to the -2 power. Remember how negative exponents work. This will be 1/25. 5 to the -1st will be 1/5. 5 to the 0 power is just 1. 5 to the 1st is 5. 5 squared is 25. So now I'm going to go ahead and plot the points I can. So -1/1/5 is going to be tricky, but I'll go ahead and plot it. Here's 0, 1. And here's 1, 5. And I do have exponential growth here. And if I was going to add in my domain and range, I'll notice that my domain again is all real numbers. And my range again, I have that asymptote along that x-axis. So my range is once again going to be y greater than 0. For the next one, we're making it a little bit more difficult. So when I make a table for this one, I kind of do a 3-tiered table because I don't want to have to do a lot of work. So I'm going to look at x, then I'm going to figure out 3 to the x power. So I'm kind of doing this in stages. And then for the last one, I'll actually figure out my y values, my 1/3 times 3 to the x power. So I have to do the first 2 rows, -2, -1, 0, 1, 2. I always know what my x values are going to be. And then if I raise 3 to those powers, I'm going to have 1/9, 1/3, 1, 3, and 9. So now I'm going to actually multiply them by 1/3. So 1/3 times 1/9 would be 1/27. 1/3 times 1/3 would be 1/9. 1 times 1/3 would be 1/3. 1/3, 3 times 1/3 is 1. 9 times 1/3 is 3. So when I am graphing, this is my x row, and this is my y row. So I'm not graphing those numbers in between. They just helped me to get my answers. There are very few graphable points. I'm just going to actually graph these 3. So when x is 0, y is 1/3. When x is 1, y is 1. And when x is 2, y is 3. And we can see our domain and range again on this one, where our domain is all real numbers and our range is y greater than 0 again. My graph looks almost kind of misleading here. I want to point this out, where I'm making it almost look like it comes back up, but it doesn't. It just gets closer and closer to that line. It's just really hard to draw that sometimes. So this might be a better graph, but again, it doesn't actually touch that line. So it's hard, especially working on a small graph with kind of a thick marker like this, to make it turn out right. So in the next one, I'm looking at y equals negative of 5/2 to the x power. So that last one, maybe we should have reviewed this really quickly. When I multiplied it by 1/3, I did a vertical shrink by 1/3. So I took that graph and I compressed it. This one, that negative, I know is going to flip over the x-axis. So instead of my graph going up like this, if I think about what it's going to look like reflected over that x-axis, it's going to look something like that instead, because of that negative. So this graph is not going to show exponential growth because I have a negative sign there. I'll still use my same x values, but I might need to show a little bit of work on this one. So if I have 5/2 to the -2 power, I know it's going to flip my fraction and it's going to square it. So this will be 4/25. And then it says negative, so negative. This might be a good time for me to do the +2 power. I know that these guys are going to be reciprocals. So this will be -25/4. And I might even have to remember what that is as far as a mixed number goes for graphing. 0 would be 1, but again, there's a negative sign, so this will be a -1. And then -1 power means I would just flip my fraction, so -2/5. This one will be a -5/2. I think I need to put lines here. This is kind of hard to read. So when x is -2, -4/25 is too hard to graph, so I'll start with -1, -2/5, 0, -1. 1 is -5/2. -5/2 is really -2.5. So let's go ahead and graph that. Let's see, forward divide into 25, let's see, 6 times. So 6 and 1/4. So 2 is down 6 and about 1/4 of a unit. So our graph is going to look like this. So let's look at domain and range on this one. It's going to be a little bit different this time. So my domain is still all real numbers. I can still use for x negatives, positives, 0, and my x's stretch the whole length of this x-axis. But now my y's are all underneath the x-axis. So my range this time, because I was multiplying all my answers by a negative sign, my y's are going to be less than 0. They're all going to be negative. For number 4, I'm looking at translations. So my translations, if we think about working with all these other shapes we've had so far, whatever, if it says x minus h, we're always doing the opposite, and the h is the one that affects us horizontally. That number on the outside that we always call k, that moves us up or down. It's always the same sign, and that's the one that's vertical. So with my first graph where it says 2 times 4 to the x plus 2 power plus 1, this plus 2 here is going to move my graph 2 units left. The plus 1 is going to move it 1 unit up. And the 2 times is going to vertically stretch by 2. So those are all the different things that those numbers are doing. So when I go ahead and make a table for this, I make a table for not this whole function. I just make a table for y equals 2 times 4 to the x power. And then once I figure out that graph, I'm going to shift the points. And I'll only graph 2 or 3 points on it, and I'm just going to shift that. So when I'm making a table for this, I want to have x, I want to have 4 to the x power, and I want to have 2 times 4 to the x power. And remember, we're graphing our x row, and then the last row is the y. We're not really graphing that middle one. It's just helping us figure this out. And even though I'm not graphing all of the points because I don't think they're all going to really fit or be practical, I'm making my table for x go from -2 to 2, just because that way I'll be able to look at the points and figure out which ones are the easy to graph ones. It's probably just going to be the ones in the middle, but you never know. So I like to include extra stuff. So 4 to the -2 power would be 1 over 16, 1/16. This one will be 1/4. 4 to the 0 power is 1. 4 to the first is 4, and 4 squared is 16. For my y row, I'm multiplying them all by 2. So let's say 2/16 would be 1/8. This would be 2 times 1/4. 2/4 is 1/2. 2 times 1 is 2. 2 times 4 is 8. 2 times 16 is 32. So yep, we're not really going to be able to graph all of our points. We're going to look at these x's. I'm trying to do it in a different color here. So I'm going to use these numbers for my x's, and these are going to be my y's. So this is going to be my original function, my parent function, and then I'm going to have to do that shifting to get my final graph. So let's see, -1 is 1/2, 0 is 2, and 1 is 8. And then I need to shift, so I'm not even going to connect this. I could connect it and just really clearly mark it, but for me, it's almost like it's easier to just not connect it, and then the teacher can tell like which one's my final graph. So now I'm going to take this point, the first one, I'm going to move it 2 left and 1 up. This one's going to go 2 left, 1 up, 2 left, 1 up. And remember, if I'm moving my graph 1 up, my asymptote moves up 1 also. So now my asymptote, instead of being at 0, will be at 1. So I'm going to go ahead and connect my final graph. It's not wrong. It's kind of ugly. Sorry about that. It's not wrong to connect both of them. You just want to make sure that your final one is clearly marked so I know which one I'm supposed to look at and grade. My domain on this one is still all real numbers. My range is a little bit different this time. I shifted that asymptote up 1. So now my range is going to be y greater than 1. Exponential growth models. So we're given a formula. A is our initial amount. Y is going to be after t years. R is our percent increase, and then 1 plus R, that whole quantity, is going to be our growth factor. So we're going to look at using some exponential growth models to find population or money, stuff like that. So first we want to know exponential growth model given the population P of Kern County T years after 1970. So let's see what we can figure out. It says in 1970, the population was about 330,000. That looks like an initial amount. From 1970 to 2000, so that's going to be our T years. Really, we could probably figure out exactly how many years, but we're just making a model. So T years, the population grew at an average annual rate of 2.4%. So using my formula, y equals A is my initial amount, 330,000. And then inside my parentheses is 1 plus that rate, which is my percent increase, and that's 0.024. So make sure you change it to a decimal. So you might even want to make a note here, as decimal. And then my power is going to be T. So I'm going to simplify it. 1.024 to the T power. And then in 1990, we want to know how many people lived there. Well, that's going to be T equals 20 because it's 20 years after 1970. So I'm going to take my exponential growth model that I just came up with, and instead of T for my exponent, I'm going to use 20. So 330,000 times 1.024 to the 20th power. And because we're looking at population, we should round this to the nearest whole person. So that would be, and on your calculator, you're going to have to do your exponent part first and then multiply by 330,000. So you should have about 530,290. For our last problem, we're going to look at money. So this is my formula for compound interest. So I have my A is my initial amount here. Principal is another word for that. That's why they're using a P in this particular formula. My rate is still as a decimal. And then N is the number of times compounded. Decimal. That does not look like the word decimal. Just trust me, it says decimal. Semi-annually means twice a year. And so let's see. That means our initial amount, the P is going to be 5,500. 0.036 will be R. 2 years, that means T is 2. And because now for this first one, I have no idea what I just clicked on, so let's go ahead and close that down. For this first one, if I'm compounding twice a year, that means N will equal 2. So I'm going to go ahead and plug everything to my formula. So A equals 5500 times 1 plus 0.036 all over N, which is 2. My exponent is N times T. So that's going to be 2 times 2. And at this point, you can just plug the entire thing into your calculator. You might want to do a little bit of work first. It turns out that I can take 0.036 and divide evenly by 2. So I might do that part first. So 1 plus, actually, I could just go ahead and add that too. So let's see, 1.018 to the 4th power. And with money, remember, we'd want to have 2 decimal places, and we're going to make sure that we round. So this would be about $5,906.82. So we're using the same P, R, and T for the second part, but now we're looking at the interest being compounded monthly. So monthly means 12 times a year. And so n is 12. So A equals 5500 times 1 plus 0.036. All of this is still the same, but now my n instead is 12. And then nt will be 12 times 2. So if 0.036, if that wasn't divisible by 12, I would just leave it. But I can actually divide that. So I'm just going to keep going and simplify a little bit to make it easier to put in my calculator. But if that worked out to be a weird decimal, I wouldn't be doing this. So this will be 1.003. 12 times 2 is 24th power. And so A will equal, remember 2 decimal places again, 5909.97. So the more often we compound, the more often we look at like how much interest is there and then add it back, and then you can gain more interest on that money. So the more you compound, the more money that you can have. But it's not really a huge amount difference, not with such a low interest rate and such a small amount of money. I know it doesn't seem like a small amount of money. It's not a small amount of money to me, trust me, but when you look at banking and how things work, $5,500 is not really a lot. These were our 7-1 notes.